Okay guys, so in this lecture we'll be continuing on seeing more on Vanderwall's equation compressibility factor. So let's get started. So our new case is when we are seeing the real gas at low pressure and let's say moderate temperature. Okay, so volume would be, so let's say we have volume as sufficiently high. Okay, and A plays a crucial role. Now we can write the equation as P plus an square upon V square. V minus NB would be just BV because V is sufficiently high would be equals to nRT. Okay. Now we can write that this is simply PV plus n square by V equals to nRT. So we said that A plays a crucial role. So here you can see that we can write. So if A is very small, then it will behave as ideal gas. But if A is sufficiently high enough, then obviously this would be a real gas. This would behave as a real gas. So we can write that from here we can write PV upon nRT plus an upon an square upon V multiplied with 1 upon RT would be equals to 1. And from here we know that PV upon nRT would be compressibility factor. So Z equals to 1 minus an upon VRT. Hence, or we can write Z is equals to 1 for a sufficiently reasonable value of A. If A is value 0, Z would be 1, hence it would be a behaving as a real gas, ideal gas. Okay. Next condition, let's say we have low pressure and high temperature. Okay, so in this case, what will happen? So V would be high in this case. Okay, because as pressure is low and temperature is high, there has to be one volume condition which has to be high. Okay, or rather, if it's been explicitly given also that volume is high, then what we can say is n square upon V square would be extremely small value. Okay, so from here we can write PV equals to nRT. Okay, because an square upon V square would be negligible term and V minus NB would be equals to V. Okay, now what happens at high pressure? High pressure is P plus an square upon V square. As pressure is already high, an square upon V square would hold less value, multiplied with V minus NB would be equals to nRT. As we can write P is very much higher than A square by V square. From here we can write PV minus PNB equals to nRT. So we can write that PV upon nRT minus PNB upon nRT is equals to 1, or we can write that Z equals to 1 plus PB upon RT. So this means that Z would be higher than 1. Okay, so let's see a graph again between Z and P. Z is the compressibility factor here. When Z equals to 1, So we have the following graph for hydrogen and helium. At 0 degrees Celsius. So this is Boyle's temperature graph. Okay, and if we talk about the graph of the same, let's say, hydrogen gas at very low temperature, we can have the graph, the same graph as something like this. Hydrogen graph. Okay, so you can see that how with the variation of temperature the graph of compressibility factor with P can change drastically. Okay, so now we will be seeing reduction of Vanderwall's equation. Okay, we will be seeing reduction of Vanderwall's equation. So we have P plus n square upon V square into V minus NV would be equals to nRT. Okay, so let's say we convert it into molar volume, V into Vm, so we would have equals to RT just divided by n throughout the equation, or rather we just divided n in this equation, so we have Vm and minus B here, and n upon V is 1 upon V. Okay, so we just wrote 1 Vm directly here. So we can write here that P would be equals to RT divided by Vm minus V minus V upon A upon Vm square. Okay, so let's multiply both sides with Vm and divide both sides with RT. So we will be getting PVm upon RT would be equals to Vm upon Vm minus B minus A upon RT Vm. Okay, so we know that PVm upon RT is nothing but compressibility factor. Okay, so Z would be equals to, so here we can more simplify it, so it can become 1 minus B upon Vm minus A upon Vm RT. Okay, so this is nothing but compressibility factor. Okay, so from here we can write that this is nothing but a summation of 1 plus B upon Vm plus B square upon Vm square and so on. So this would just be a geometric sum of these values minus A Vm RT. Okay, so from here we can write that 1 plus 1 upon Vm B minus A upon RT plus B square upon Vm square and so on would be Z, or compressibility factor. Okay, so from here we can write this thing into something like 1 plus capital B upon Vm square plus upon Vm, plus we can write C upon Vm square and so on. So B and C are nothing but virial coefficients, where B would be B minus A upon RT, and C would be B square. Okay, so this is second virial coefficient, and this is third virial coefficient. Okay, so just remember this. Some of the questions may be asked on the top of this, wherein you have been given the value of second virial coefficient or capital B, and the value of third virial coefficient or capital C, and you have been asked to find out value of A and B, and using the same you have to find out some more things like what is the pressure when volume is given and temperature is given of a real gas. Okay, so for finding the pressure you need the value of A and B as well. So A and B values can be found out from the given values of virial coefficients. Okay, and those values then can be put on to the Vanderwall's real gas equation to find out the value of pressure. Some questions on these lines may be asked in the examinations. So till then, um, we are done with this lecture, so we'll meet in the next lecture. So till then, good luck and goodbye.